Swayam Prabha. Digital India. Educated India.
Welcome to Module 2, Lecture 3. We will continue from where we have finished in the last class. That is, in the last class we talked about fineness modulus at the end, and surface modulus we will define today. In addition to this, we will look into properties of aggregate, namely strength, toughness, hardness, specific gravity, bulk density, porosity, etc., thermal properties and impurities. And lastly, we will look into aggregate blending. So, let us look into fineness modulus. If you recall, yesterday or last class we are talking about average size, description of aggregates. How do you describe? One way is the grading that we have mentioned, in which you talk of proportion of aggregate in each size group, which we represent by square sieves. So, proportion in each size group, that is what one of the ways of representing the aggregate size distribution. Through sieve analysis we determine that, and another way of through a single parameter describing the aggregates is in terms of what is known as fineness modulus. Similarly, surface modulus is another characteristics. So, fineness modulus, let us look at it first. First of all, average size cannot be expressed by arithmetic mean. So, you can't express it by arithmetic mean, because sizes varies logarithmically, sizes vary logarithmically, right. Sieve sizes vary logarithmically. In other words, it actually varies in geometric proportion, like minimum size is, let us say, 0.075 mm, next size is double of it, 150.15 mm or 150 micron, then would be 300 micron or 0.3 millimeter and so on. So, you can see that this is 2 into 0.075, this is 2 into 0.075. So, it varies in geometrical proportion, geometrical progression, it varies in geometrical progression. So, if you take log of the sizes, log d, let us say d 0, let me call this as d 0, this as d 0, log d 0, this will be log d 0, this will be log of 2 d 0, and this will be log of 4 d 0. So, there is a in log scale they will vary in arithmetic progression, because every time you are increasing log d 0 plus log 2. So, this can be written as log d 0 plus log 2, this will be written as log d 0 plus 2 log 2 and so on. So, it varies in arithmetic progression in logarithmic scale, right. So, sizes varies, it is in geometrical progression, and therefore, it varies logarithmically. So, when we talk of size, when we talk of average size, we do not talk of average particle size, but what we talk of is average sieve number, and fineness modulus actually represents average sieve number, What we can do is we can define sieve numbers as, for example, 0 sieve number 1, sieve number 2, etc., etc. So, this may corresponds to 0.075 mm, this may corresponds to 150 mm sieve number. So, this is sieve number, this is sieve number, sieve number 0, 1, 2, 300.1, 0.300 mm, sieve number 2, etc., etc. So, I can talk in terms of average sieve number. So, if it is 3, average value is 3.5, which would mean that the average sieve number is 3.5. So, that is what we do, weighted average. So, we find out average sieve number, and fineness modulus represents actually average sieve number. So, we find out weighted average as proportions of particles in a given size are not same. For example, proportion in sieve number 0, proportion in sieve number 1, proportion in sieve number 2, or sizes corresponding to sieve size, I mean particle size 0, size number 0, size number 1, size number 2, proportions will not be same. So, therefore, if they are same, then my average would always be, for example, if there are 5 sieves, 4, 5, average would have been simply sum total of all of this divided by 5. But actually proportions on these ones are not same, therefore, we talk in terms of weighted average. So, if we know P 0, P 1, P 2, P 3, etc., as the fractions of particles in 75, 150, 300, 600 micron sizes, etc., then they can be used as weights for weighted average. So, P 0 is the proportion. So, P 0 into 0 plus P 1 into 1 plus P 2 into 2, etc., etc., P 3 into 3 and so on. I can sum this up, and this sum would nothing but the weighted average, because this is a fraction of the mass in corresponding to 0 size, the 0 number size corresponding to first size, second size. So, 0 size, 1 size, 2 size, 3, etc., etc. Since this is a fraction of the total mass fraction, therefore, they represents weighted average. So, they are used as weights for weighted average, right, they are fraction. So, sum total of P 0, P 1, P 2, P 3, P 3, sigma P I is equals to 1, sigma P I is equals to 1. Therefore, this represents nothing but weighted average sieve number, weighted average sieve number if I start my numbering from 75 micron or 0.075 millimeter itself. So, fineness modulus is that. So, fineness modulus, since size varies logarithmically, weighted average can be obtained as sigma of the whole thing. Actually, there is a bracket here. So, you can call it sigma P I log d I divided by sigma P I, that is what it is, the sum of this. That means, varying for I varying from 0 to n maybe. So, first one will be P 0 proportion, not proportion, log d I, the mass, this could be even mass. You can talk in terms of even mass, instead of P, if I talk of m I, this will also do, because m I divided by sigma m I, m 0 divided by sigma m I, m 0 divided by sigma m I is equals to P 0. So, this could be m, but otherwise one can have sigma P I also is correct, this is no problem, because this is will be always equals to 1. So, this is the weighted average, this is the weighted average. So, we can find it out in this manner. So, average sieve number can be written as 0 P 0, 1 P 1, 2 P 2, 3 P 3, they are the mass fraction of particles in 75, 150, etc., etc. This is fineness modulus. So, this is called fineness modulus, right. And if you look at this, this can be written as cumulative percentage retained divided by 100, sum of all the cumulative percentage retained, sum of cumulative percentage retained in all the sieves divided by 100, right, this is percentage. Thus, fineness modulus represents weighted average sieve number in which your particle belongs, all right. Let us see how it is cumulative. For single sized particle, fineness modulus of ith size will be simply sieve number itself, right. So, because there is single sized particle, so this value is 1, fraction is 1. So, it is the sieve number itself. So, 75 micron Fm is equals to 0, for 150 micron Fm is equals to 1, single sized particle, and so on. And from this, so 0 for all particles being, I can write it in terms of A B log 0.075, and as I said, logarithmic of the size sieve size or logarithm of the size of average sieve size is arithmetic, is in arithmetic progression. So, this increases simply by log 2 b log 2. Therefore, I can derive an expression for fineness modulus for a single particle size for 75 micron size. This is the fineness modulus is 0. For 150 micron sieve, fineness modulus, particles, all particles belonging to 150 micron, fineness modulus is 1. And from this, actually I can derive out A and B. A comes out, B comes out to be 3.32 and A comes out to be 3.73. So, starting from 75 micron size, Fm is given as 3.73 into 3.2, because B is 3.232, 3.32 log di. Di is the nominal sieve size in millimeter. For any size, you can find out fineness modulus like this, and for combination, fineness modulus is given by this formula, as we have seen. For mixed, number of particles, there are some particles in 75 micron. So, for cumulative, we can write it like this: 1 P 1, 2 P 2, these are the proportions, and n P n. Now, this if I break it up, I can write it 0 P 0 plus 1 P 1 plus 1 P 2, 1 P 3, etc. The second term would be 1 P 2, because there is a 2 here, and rest all this 0 is does not matter, this is only 1. This appears twice, so I can write it 1 P 2 plus 1 P 3, etc. And next series will start from 1 into P 3 to 1 into P n, and last term will be P n. Now, what is this? What is this? This is the proportion of all the particle, right. So, particle retained in bottommost size, particles retained in smallest size, that is 75 micron. This is particle retained in, this is particle retained in, this is particle retained in not 75, 150 micron, 150 micron. This is retained in 300 microns, because it starts from P 2. So, 75, 150. This is particle retained in 300, and this particle retained in the topmost sieve. So, therefore, this is the summation of particle retained in the bottommost sieve to the topmost sieve. So, this is nothing but cumulative percentage retained in all the sieve. Sieve number 1 plus cumulative retained in sieve 2, cumulative retained in sieve 3, cumulative retained in sieve n. So, this is the sum total of not cumulative percentage retained in sieve 1, percentage retained in sieve 2, not. So, all retained in all the sieves. This is retained in nth sieve, this is in the n minus 1, etc., etc. So, first one is percentage cumulative retained on sieve number 1 bottommost to cumulative retained to everything. So, therefore, this is nothing but sum total of cumulative percentage retained in all the sieves, right, cumulative percentage divided by 100, because these are in percentage, that will give you the fineness modulus. So, from the definition, fineness modulus can be derived in this manner. We calculate out fineness modulus on the basis of cumulative percentage retained on all the sieves divided by first sieve. You take how much is the cumulative percentage retained, then you find out what is the cumulative percentage retained on the second sieve, third sieve, fourth sieve. So, cumulative percent from top you can start. If you start on the top, it is the last top sieve only where cumulative, the percentage retained, that will form the cumulative. If you go to the next SIB, then that retained in top SIB and the next SIB, these two sum is the cumulative percentage retained. You go to the third next bottom one, so it will be the top, next and next, the sum total of all the particles retained in the top 3 SIBs, that will form the cumulative percentage retained. In this manner, you calculate out cumulative percentage retained in all the SIBs, sum them up, divided by 100, that gives you fineness modulus. Actually, it represents average SIB size of the particle, average size of the SIB size, not size, average size of the particle. And you want to find out corresponding average size, you can find out using the formula that I have given you, that must be equals to A plus B into log of di, I mean log of d0. So, you can find out what is the log of di. So, you can find out what is the di value, what is the average size value, you can get some idea. But we rarely use this size, what we use is the average SIB number, that is the fineness modulus, right, to represent, because it is essentially used for comparing two aggregates, which is finer, one is finer, another is less fine, right. And this is used in mixed design, some of the mixed designs, because you can designate a particular graded aggregate according to their fineness modulus. Similarly, there is another one called surface modulus, another index called surface modulus. Specific surface can be related to surface modulus. Specific surface of a sphere is 4, or if you write it pi d square is the surface area divided by 1 by 6 pi d cube. So, this will be simply 6 by d. For a ith particle size, it is 6 by di. So, specific surface for sphere you can find out in this manner. Specific surface is surface area per unit volume. For two SIB sizes di and di minus 1, I can talk in terms of average SIB size, geometric mean. So, geometric mean is the root over of these two. So, for two SIB sizes di and di, specific surface is 6 of the geometric mean size, and that is given by this. Since d I plus I minus 1 is there, d I plus 1 is 2 di, which is equals to 4 d I minus 1. So, d I plus 1 is equals to 2 d I equals to 4 d I minus 1, right. So, as the SIB size increases, right, as the SIB size increases, what will happen to the specific surface? As SIB size increases, the specific surface will, as the SIB size increases, specific surface will reduce by a factor of 2, right, because it is simply proportional to 6 over inversely proportional to di. So, if you have higher d size, specific surface will reduce by a factor of 2. So, considering contribution of size fraction, all size fraction, I can write it therefore, surface modulus as, this is the size fraction of the bottommost SIB, that is retained in 75 micron passing through 150, and this is the P1, P2, P3. So, size contribution will be proportional to, so if I write this multiplied by d, the smallest size d0, that will be the, that would give me the total, some approximate value of surface, specific surface of the aggregate. So, that is how surface modulus is defined as 2 sigma pi divided by 2 I. If you expand this, that is sigma p I divided by 2 I. So, I can write it like this, it is I going from 0 to n, first one will be p 0, right, I mean this will not be valid, p 1, it should go from p 1. So, first one is p 1 plus p 1 by 2 and p 0 comes otherwise. So, p 0 divided by 2 I 0. If you I put 0, then there is, of course, it will be infinity not defined, P 1 plus P 2 by 4, etcetera, etcetera. So, let us generalize it in this manner. So, surface modulus is defined by this multiplied by d 0 will give us the total surface area. Now, SIB 0 to 1 is average SIB between 0.75 and 150. So, this corresponds to 533 when it is in millimeter, size is in millimeter. Next, for next level 1 and 2, it is 533 by 2, next level. So, therefore, specific surface of all aggregate will be surface modulus multiplied by 533, because surface modulus is defined as this term. This multiplied by the specific surface of the smallest group 0 to 1, it gives you 533. Now, this is for spheres, because we have used d by 6, d by 6. For actual aggregate, angularity factor can be introduced, and therefore, specific surface is given by 533 by angularity factor, which we have defined earlier, right. So, this is what is surface modulus, because for irregular shaped particle, for circle, this is the surface area is minimum. For irregular shaped particle, surface area will increase. So, 1 by xi, which increases with irregularity or angularity, this will be the specific surface. So, from surface modulus you can calculate out aggregate surface area, specific surface of aggregate, that is area per unit volume, get an approximate idea about this. Some of the mixed design method uses surface modulus as a parameter to define the kind of compare two different aggregates. Well, surface area is important, because more the surface area, more water you will require for wetting the aggregates, but perhaps packing characteristics is more commonly used, because that seems to be more logical. So, therefore, packing characteristics is used more often than surface modulus. Some of the mixed design concepts uses surface modulus, this index, for finding out the proportions of aggregate, etcetera, etcetera. Okay, now, the properties of aggregates. The strength of aggregate is measured, through aggregate crushing value, because you see parent rock strength is usually not relevant in case of concrete, because once you fracture the parent rock, its strength would be higher, because fracture has already taken place through the fracture planes. So, whatever is remaining must be stronger. Well, size effect sort of thing, larger the size, probability of finding a failure plane or fracture plane is more. Therefore, no point using rock strength in aggregate. Second issue is, you see, the aggregate, if they are in aggregation forms, it is very difficult to measure their strength as such. So, what we do is, we compare two aggregates, we use a test called crushing value test. There is another similar test called impact, aggregate impact value. So, crushing value test is very commonly used. In this one, what we do is, we pass aggregates through 14 mm sieve and retain on 10 mm sieve. So, only this size we take, effect of size is actually eliminated. This is oven dried for 4 hours. So, moisture condition is again more or less finalized, fixed, standardized, and then crushed under 400 kilonewton in 10 minutes. So, the rate of loading is also fixed. Now, what will happen when you crush this ones aggregates? Originally, it was something like this filled in, right, and once you crush, they will occupy these areas, only this first, but they will have number of fines generated through crushing. So, then you sieve this material through 2.36 millimeter sieve, and percentage passing is recorded. 25 to 30% means good aggregate. If it is high 40-45%, then it is not so good aggregate, comparatively 25 to 30% is good aggregate. So, can be used in concrete. So, therefore, this is used to measure relatively, compare two aggregates relatively, and also to specify to use in specification. That means, you specify that aggregate crushing value which is expressed as percentage should not be more than 32 or something like that for use in structural concrete and so on and so forth. So, relative comparison, one having lower crushing value is better compared to one having higher crushing value. You see, then there is another way of testing the same one, that is load required to produce 10% fine is another variant of this test. So, in this one we find out percentage passing, but in another variant of this test we try to find out the load required to produce 10% fines, right, load required to produce 10% fine. What is done is progressively load is increased to obtain penetration in 10 minutes, right. So, then this should be 15 millimeter for rounded aggregate. So, this penetration is specified, increase the load such that you get a penetration of 15 millimeter in 10 minutes. So, this if you get a penetration, these are your aggregates. So, the change new, here is your new aggregate after crushing, this should be 15 millimeter for rounded aggregate, then 20 millimeter for crushed aggregate, already crushed aggregate, because this will have still some failure plane, this will have less. So, this is what you do. 20 millimeter for honeycombed aggregate, we have looked into honeycombed aggregate when we talked of shape. So, this is what is given, and then percentage passing through 2.36 millimeter sieve is found out, should be between 7.5 to 12.5%. And let us say we got y for load x. So, the load is unknown here, you try to find out how much is the load required to achieve this much penetration or this much penetration or this much penetration, depending upon type of aggregate. And let us say the load is x for a penetration of y, not penetration, y percentage passing through 2.36% sieve, 10% fines, because you want to find out how much will be 10%, what is the load required for 10% fine. So, supposing you have found out 7.5% is x load. So, 10% fine value is given by this 14 plus y by 4. So, y you found out at a given load, right, y you found out at a given load x. So, for x you found out for y percentage is for x load, 1% is for y by x by y load, right, but y plus 4 is used, y plus 4 is used. So, this into 14. So, that gives us the 10%, right. So, this should be 10% fine, 10% fine. So, here 10 plus 4, y plus 4 and 10 plus 4. So, it is assumed that things 4 mm you will be just getting straightforward, after that it varies linearly. So, 14 y plus 4, y is what you have found out, and 10 plus 4 is 14. So, this is the relationship used to find out the 10% value, and this is also used as an yardstick for comparing two aggregates, used as an yardstick to compare two different aggregates. Impact value is also measured on the same machine. You take materials passing through 14 millimeter sieve and 10 mm sieve, all these are specified quantity, etc. The aggregate should be in saturated dry, surface dry, and now only thing you have a standard hammer falling 15 types under self load. So, you have a hammer which is lifted up and down, it is just lifted up and down. So, under self weight that hammer mass falls through a standard height 15 times, and then find out how much is the percentage passing through 2.36 mm. So, then you sieve it through 2.36 mm and percentage passing is recorded, 25, 30, 45 for concrete floor pavement, for concrete 25 is recommended for concrete, for floor 30, pavement and other use 45%. So, aggregate impact value, 10% fine value and aggregate crushing value, these are the measures for strength relative, these are used for relative strength comparison of aggregate, and it must satisfy the minimum required. Otherwise, strength of the concrete will be limited by aggregate itself. In normal concrete, strength of the concrete is not limited by aggregate, because aggregate rarely fails, as we shall see later on. Aggregate abrasion value: particles between 14 mm and 20 mm are bonded using standard setting compound. So, you want to find out the abrasion value, quite useful in case of pavement and flooring, where you expect a lot of abrasion will be there. Abrasion is caused by standard grinding and lapping through 500 revolution with a single size standard sand. So, you cause abrasion through sand of single size, right. So, this do what is called lapping and grinding, and percentage loss of mass is a measure of abrasion resistance. So, you grind it putting sand on top of it, and once you have done that, some of the aggregates will become powder, loss of mass will be there. So, loss of mass is measured, and that gives us abrasion resistance. Lower it is, better; lower the mass, better is the abrasion resistance. Los Angeles test is another one, which uses steel balls and standard graded aggregate rotated together in a drum in a standard manner. So, there it was sand through which you are grinding. In this case, you have steel balls and the aggregates, they are rotated in a standard drum in a standard manner, and percentage loss of mass is measured, and that gives us abrasion as well as attrition. Specific gravity. Specific gravity, pycnometer can be accurately filled up to a specified volume. Supposing I have got a bottle or something like that, and which I can fill in up, I can close it possibly, something like this. I have a seal, lead is there, and I can fill it the water up to some specified volume. Then D is the oven dried weight of the aggregate. So, mass of this pycnometer full of water, that is C. So, first I found out what is C is the mass of the water full, mass of the meter with sample and water, that is B. Now, you remove some, you put this oven dried aggregate, and all the time you will have water filled up to same height. So, remove water such that it fills only up to the fixed height all the time, that is volume is fixed. So, let us say that mass is B, right. So, B is equals to D plus W, that is D plus some weight of water, C is equals to weight of water, this W, plus weight of same volume of aggregate, weight of same volume of aggregate. So, B minus C will give you D minus WA, that means that is the mass of the aggregate, oven dried mass of the aggregate minus mass of the same volume of water. The apparent specific gravity, therefore, one can calculate out D divided by D minus B minus C, because B minus C is this. So, if you subtract from D, you get the mass of water of the having same volume. Now, if you are doing it in CGS units, that is centimeter grams per cc. So, then in that case simply specific gravity you can find out without deviation or anything of that kind. Simply D will be D divided by specific gravity will be D divided by D minus B minus C. This includes impermeable pores. The D specific gravity is not specific gravity of the material, but it is apparent specific gravity, because the pores which are not filled by water will be considered as solid in this sort of measurement. Sometime wire jacket method is used to find out the specific gravity of coarse aggregate. That means, you have a jacket, fill in the mass, put it in water. So, see the volume of water displaced, from that you can find out, you take again weight in the submerged condition. So, from that you can find out accurately volume of water displaced, and then find out the specific gravity. The basket has apertures as 1 to 3 millimeter, is suspended from a balanced to watertight tank, and let us say D is the oven dried weight. Mass of empty basket in water is C, mass of aggregate and basket in water is B. So, B minus C is the mass of aggregate in water, and that is the loss in weight. So, apparent specific gravity will be 1000 d divided by d minus B minus C, because if everything is in kg, then you have to multiply it by 1000 in order to get the specific gravity. What you are doing? You are using simply Archimedes principle. The mass of the, that there is a loss in weight of the material when you submerge them in water, and the loss in weight is equals to the mass of the volume of water displaced. So, using this concept you can find out the specific gravity using this formula. Again it includes all pores, impermeable pores as well. So, this varies from 2.2 to 2.6 to 2.7. Okay. So, A is the absorption basically. If A is the mass of aggregate in SSD condition, bulk specific gravity is sometimes given by this A, bulk density you can say. Supposing I find out A is the mass of the aggregate, A minus B minus C in the same manner, you can call it bulk specific gravity, where A is the mass of aggregate not oven dried condition, but in what is called saturated surface dry condition. We will look into saturated and surface dry condition quickly. Saturated surface dry condition refers to situation where absorbed moisture is present inside while surface is dry, and that is a standard condition used, because it is very difficult to control them, like define or standardize the moisture content. But saturated surface dry, that means inside there is water, outside surface is dry, that you can find out by wiping of the water from the surface using a flannel cloth or something of that kind, or even by visual observation. While drying sand, the color would change suddenly from wet to the dry state, surface dry state, right. So, water absorption is measured with respect to oven dry condition, always we do that. Free water is the water content in concrete that excludes water required for SSD condition, because SSD condition, saturated surface dry condition, is considered to be the standard in case of concrete, because water will be absorbed by the aggregate themselves. Now, this water has to be taken into account in adding water while we add water for mixing, because this water will not be available neither for reaction nor for mixing purposes. So, we exclude out water which is absorbed inside the aggregate. So, surface dry and water inside, that we call as saturated surface dry condition, and it is the standard condition that is used for moisture content, content of aggregate in concrete production as well as mixed design. This illustrates what is SSD condition. This is bone dry, fully oven dry situation, there is no water, there are pores, no water. If you come to this, this is air dry, that means the air surface has dried out fully up to certain depth, but moisture is still inside. If it is saturated surface dry condition, there is moisture inside all through, but surface there is no moisture, and moist is even outside you will have a layer of water. So, this is our standard condition, right. So, these are absorbed moisture and this is also absorbed moisture. This is somewhat, it will have some free moisture from this point to this point, excess water outside, and we do not in our standard condition you consider this, because this is a fixed condition. This might vary depending upon porosity, this might vary depending upon porosity, but this is the standard condition, and the water now inside will not be available for, it will be absorbed by the aggregate and will not be available for reaction. So, therefore, that is why this is used as a standard condition, saturated surface dry condition. This can be determined by drying from saturation, signifies by a color change, or by drying with thick coarse cloth. So, you take thick coarse cloth, flannel or something of that kind, wipe off the water from the surface, and that is SSD condition. Then volume changes due to frost action, thermal action and wetting drying relates to soundness. This is also somewhat measured. Bulking is increase in volume with moisture for sand, it is only for fine particle, because particle will absorb, sand particle can absorb moisture. Sand particle can absorb moisture. It can absorb moisture in the surrounding. Sand particle can absorb moisture in the surrounding, right. So, sand particle can absorb moisture in the surrounding in its outside periphery. It can actually absorb moisture. Now, when it absorbs moisture, its effective size increases. So, initially there will be pushing of the particle, but a time comes when all this water collapses and particle then comes close to each other. So, if you plot volume for a fixed mass, then you get this sort of curve. The volume increases with moisture content of sand. It increases, picks up a peak and then it is reduces. So, this is called bulking of sand, it becomes bulk volume increase. Well, this has got do not have much to do because we do not use volumetric mix design, but one must remember this because it will change the packing characteristics. Particle size becoming larger, it will change the packing characteristics. So, this is important from that point of view, otherwise bulking is not very important because in mix design we do not use volumetric batching. In earlier days, quantity, the amount of moisture content corresponding to bulking was an important issue because volumetric batching was done. So, you have to add a correction in terms of volume. Since you do mass basis, these are all not required and you always consider the aggregate in SSD condition. So, this issue is not so relevant. Thermal conductivity is an important property and its coefficient of thermal expansion of concrete, it depends largely on aggregate. Thermal conductivity of concrete is a function of aggregate thermal conductivity and it would depend upon type of aggregate and moisture content. Cement paste has a thermal coefficient of thermal expansion as 5.5 into 10 to the power minus 6 and aggregate has got different and it should be compatible with the cement paste for durability. So, generally order of concrete thermal conductivity is maybe 6 to 20 into 10 to the power. Thermal coefficient of thermal expansion is of this order per degree centigrade. Thermal conductivity is might vary from 1 watt meter degree centigrade or degree Kelvin to about 2.5 or 3 watt meter degree Kelvin depending upon aggregate type. Maximum is for quartz or quartzite. Now, important aspect is deleterious materials. I was telling you that finest size we take, aggregate size we take is the sand. Finer than that size like silt etc., they are harmful in concrete. The reason is silt always has a tendency in this very fine size. So, it has got kind of forces, surface forces and which will actually make it to get stuck to the aggregate surface. So, silt, clay etc., they will get stuck to the aggregate surface and if cement will not be bonded to the aggregate. So, these are important ones, but besides that there are some other deleterious material. Impurities which interfere with the hydration process like organic matter from decay of vegetable such as humus are deleterious materials. This is tested by observing the color change while neutralizing with 3% sodium hydroxide. Dark color after 24 hours indicate organic impurities. So, organic impurities are tested with alkalis and the color change tells us because they organic impurities they can react with alkalis and color change tells us whether there is a organic impurity, deleterious organic impurity in the aggregate, right. You see, this is why clay we do not want. Clay prevent coating and development of good bonds. Silt also does this a little bit, but also it will increase a lot of water demand because it is very fine. So, if you are trying to use silt in the aggregate system or there is too much of silt, let us say more than 3.5% or something like that, then it will have a tendency to absorb a lot of water. Clay wood obviously do not allow any bond between the aggregate and the cement hydrates. So, actually the strength would be lower. Weak and unsound aggregate themselves are harmful. So, weak aggregate means aggregate crushing value very high, you would not like them, and unsound aggregate means which themselves will expand in volume, they will cause cracking of the concrete. Maximum deleterious substance should be 15% in crushed rock fines and 10% for all crushed aggregates. 3% of crushed rock, partially crushed rock or partially crushed sand, these are the limits, and percentage passing through 75 mm sieve should be less than 3% by mass of sand. This is the silt or clay, this should be less. So, these are percentages are given. For sand, clay, silt and fine dust is determined simply by decantation. You put it in a jar, measuring flask, and wait for long period of time, you will find that silt will settle at the top because it is the finest size, sand will go at the bottom, and the color distinction, from color distinction one can find out what is the percentage of particles finer than 75 micron, and that should not be more than 3%, should be less than 3%. Well, you can do wet sieving to find out, do sieve analysis for coarse and fine aggregate, and salt contamination due to soluble chloride or salt causing efflorescence can be removed by washing. So, if you put, for example, aggregates in water for some time, and if I find color is white efflorescence or salt getting deposited at the top, that would be some sort of leaching or efflorescence. By washing they can be removed. Unsoundness, that is volume changes, are due to non-durable impurities, disruptive action during freeze thaw action, this is what, and clay lumps of shale, if they are there they will expand in volume. Wood coal leads to pitting and scaling, these are unsoundness. Mica and gypsum sulfates and sulfides shall be avoided. Some they result in kind of unsoundness, in the sense there will be expansive changes, durability properties will be hampered, and disrupting action during freeze thaw actions could be there. So, we do sieve analysis, as I said earlier, to find out the grading, and this is the sieve analysis, typical sieve analysis result. What it shows is percentage passing versus size, 175 micron, 150, 300, 600, up to 10 mm size it is shown, 100% is going along, passing along 10 mm and so on. This is for sieve analysis or grading curve for 10 mm MSA aggregate. This similar things you can plot for 20 and 40 mm also, and this is in ASTM sieve number or size, it is in inches, 3/8 inch, then 4 numbers, 8 number, 100 number, 200 number sieve. This is normally the standard, most of the standard uses this. Well, to get a good grading, you may have to blend aggregates. For example, you have 150, let us say 150, there is a sieve, cumulative passings to 150 mm is 100%, to 75 is 55%, to 40 mm is 20, and 20 mm is 13, and 10 mm is 5. Let us say available grading, this is what is my desirable grading. Just as an example, how do you do blending? I want 100% should pass through 150 mm sieve, 55% should pass to 75 mm sieve, 40% should, 28% should pass to 40 mm sieve, and etc. What is available to me is 98% passing through 150, 10% passing through 75, this is grading 1, and this nothing passing through this. And I have got second aggregate 150, 100%, 75, 92, which is 46. nothing through 20 and 10, and then I have got third sieve 150, 100 and something available here also. And if you can see this fourth one which has got large number of fines. So, these are finer particles, less fine, still lesser fine, and this is the coarser one, this is the coarser one, and I want to get a blended aggregate of satisfying this desirable grading. So, what I do? I have got 4 aggregates, graded aggregates, and I got to mix them, right. I got to mix them to find out the desirable grading. So, basically proportion of each one I must have. So, let us say A, B, C, D are the proportions of 1, 2, 3, 4 aggregates. Then at 75 mm micron on 75 mm size here, if I take if you look at this one, first one 75 mm sieve, only 10% passes. So, if I take A amount of this aggregate 1, its multiplied by 0.1 will be the quantity of 75 mm available to me. Similarly, if B is the amount of aggregates I take from grading 2, available grading 2, so this multiplied by the corresponding value, that is 0.92. So, this multiplied by 0.92, and similarly for C and D, that would be the quantity of materials passing through 75 mm. How much I should have? This must be equals to 55% of my overall. So, 0.55 of A plus B plus C plus D. So, I can set an equation at 75 mm size, and this is what I am trying to do, and this is what I am trying to do. So, I am trying to put an equations for 75 mm size, 0.1 A, 0.92 B, 1.0 C, 1.0 D, because that did not 100% was passing through them, must be equals to 0.55 A, B, C, D. Similarly, for 40 mm size, there is hardly nothing for A, only 6% for B, 0.94% of the C aggregate passing through 40 mm, and 100% passes for D aggregate, and desirable is 0.28. I can set a third equation. Now, I must set 4 such equations, because I have 4 unknowns. So, for 20 mm, so I had actually 150 mm, I had 75 mm, 40 mm, 20 mm and 10 mm. So, for 4 such ones I can set 4 equations. Here of course, we have done one thing, we have assumed A equals to 1. So, that 1 is eliminated straight away. So, I need only 3 equations, right. So, if I assume A is equals to 1, because if I assume A equals to 1, rest all can be obtained as a fraction of A itself, right. So, assuming A equals to 1 for 75 mm size, this is 1 and this is right, it will be given. So, I get an expression involving B, C and D if I assume this equals to 1. Similarly, for 40 mm size, I will get an expression involving B, C, D, and for 20 mm size I will get an expression using B, C, D, and I can solve them. I can solve these 3 equations. So, these are the 3 equations I am getting. Well, I could have solved 4 equations also, it is not difficult, because it is question of matrix. So, simply solving the 4, like A, B, C, D are your unknowns. You had a matrix on this side, the coefficients are known, etc. A 1 4 and so on, A 4 1, A 4 4, and that is the right hand side is known to you. So, you just got to invert the matrix or solve it. These days it is not very difficult to solve it in Excel, and that is what you can do. However, by conventional wisdom of the old days, one would actually solve this 3 by 3 unknowns can be solved by Gaussian elimination process, or 4 unknowns can be also solved by Gaussian elimination process. So, that means divide the equation 1, if these are the 3 are the case, just for example purpose, divide this by 0.37 and multiply equation 1 by 0.22 and add and 0.13, right, and this divide by 0.37 multiplied by 0.22 and multiplied by 0.13 and simply add, you will eliminate out b, right, and if you do that, you eliminate out b, the equation then get is something like this. Then you take pivot this element, divide equation 2 by 0.93 and multiply equation 2 by 1.216 and subtract, and 0.068 and subtract from equation 1 and 3, and this will lead to B C equals to this. Then the next step would be divide this equation by 0.88 and you get the value of D. So, multiply this by 1.060 and subtract from this, then you will get straight away value of C, and if you do this process, you get BCD equals to 0.22, 0.29 and 0.28. You have assumed A equals to 1. So, ABCD proportion of this is 1.5, 0.52, 0.29 and 0.28. So, proportions is what we are looking at, therefore, ABCD proportions we can get. So, aggregate blending can be done in this manner simply and obtain, you will get 4 equations. One of them of course, you can assume to be 1, because you want to find the proportion of all the 4s, 4 of them or 5 of them depending upon how many aggregates you have. So, if you have 4 aggregates, what you do? You set 4 equations at 4 important points and then 4 equations, because you know the proportion of desirable grade for desirable grading and proportion in each of the grading. You can sum this up, and by summing up get you can form those equations, assume one of them equals to 1, rest all then you can determine, and this is how you can find out the proportions. So, you can find out the proportions, right. So, you can find out the proportions. So, from this you can actually determine, because now if instead of 1 relative proportion you want to find out, you will find out 0.48, 0.48 for A, because this was 1 divided by the total. So, this is the 0.48% will be the A, multiplied by 0.52, 25% will be B, 14% multiplied by 0.29 will be C, and multiplied by 0.28 will be almost similar. So, this is the proportions of ABCD, right. So, this is how finally therefore, I get this by solving this equation, I get 150 each one of them. This is the proportions of each one of them will be this, and blended aggregate quantity I can calculate out, because I know 150, this is my desirable, 98 into 0.48, 100 into 0.25, 100 into 0.14 and 100 into 0.13 gives me 99.04, 10 into 0.48, 92 into 0.25 and 100 into 0.14 and 100 into 0.13 will give you 54.8 and so on, and if you calculate out all of them, you get the blended aggregate. So, therefore, total you can find out, and this is how you can obtain the proportion of all the aggregates. So, therefore, this is how we find out the proportions of aggregate, right. So, to summarize we have actually in this module 3 we have looked into aggregates, packing characteristics, tests, some index like fineness modulus and surface modulus. But in the beginning we also defined how do you define size, shape, because and they are important in packing we have looked into. Some of these ideas will be very useful when you discuss workability and other issues. Thank you very much.